This lesson follows naturally from our last lesson, which was realizing that the sum of any power series was a function. And if that's the case, then we can do operations on our power series. And if we do the same operation on our function, we'll have a new function that is the sum of the new power series that is the result of whatever that mathematical operation was. So let's suppose that S of x is the sum of a power series on some interval I, very close to the point around which the power series was built. So here, S of x equals our power series. Then, on that same interval, whatever operation we do to our function, we also do to our series. And the resultant power series, we're guaranteed, will be the power series that is the sum for. And we can do any mathematical operation we want. For us in calculus, we're interested in differentiation and integration. So since S of x is a function that is the sum of that power series, if we take the derivative of our function and we take the derivative, and we can do it term by term, whatever the terms are in that power series, we just use the power rule for differentiation on every term. And the result of that is going to give us the new power series that this function is the sum for. So if I take the derivative of a constant, it goes away. I get 0. The derivative of this term with respect to x is a sub 1. Pop my power down front, reduce my power by 1. So you can see where all of these terms come from. So that's how it works in general. Of course, our power series will have actual numbers for a sub 1 and a sub 2 and so on. And it works just as well with any other mathematical operation. We can integrate our function. A note on notation. Your function probably in that setting is going to be written in t. It's going to be written as f of t dt. But when we find the antiderivative of that, I'll call it capital F, and we do fundamental theorem, then we'll wind up with some function in x. That's just a notation issue there. But whatever we do to our function, we also do term by term to all of the terms in our power series. And if we do that same operation, then we're guaranteed that this will be the power series for that resultant function, or that resultant function will be the sum of that new power series. So let's look here term by term. Let's compare what's happening here with the power rule for integration. If I integrate a naught with respect to x, I get a naught times x. If I pop a sub 1 out front and integrate x with respect to x, I get 1/2 x squared. So you can see that integrating term by term, just like differentiating term by term, is going to work for us. That's the power of polynomials. That's the reason that all of our approximating polynomials were polynomials. And then with infinitely many terms, our power series behave like polynomials. So we differentiate and integrate term by term, because both of those mathematical operations break up over addition and subtraction. Okay, so pretty straightforward. So let's say we're given the power series for 1 over 1 minus x. We know that 1 over 1 minus x is the sum for this power series. Here's the power series representation for this function. Very near our target point that we built around, which obviously here is 0, very near 0, this function and this power series behave exactly the same. So how can I start from this power series and find the power series for that function? Well, what I need to do is compare these two functions and find out what mathematical operation was done on this one that yielded that for an answer. And whatever was done there, as long as I do that same operation on this side of the equal sign, then I'm guaranteed that that result will be the power series representation for that new function. So what is the relationship between these two functions? Well, this one is the derivative of 1 over 1 minus x. Let's verify that. If I'm going to take the derivative of that with respect to x, the negative pops down front. I reduce the power by 1, and the chain rule says times the derivative of what's inside. This is the quantity 1 minus x to the negative 2, which is equivalent to 1 over 1 minus x to the positive 2. So I know now that I need to differentiate term by term every member of the power series for 1 over 1 minus x. So the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared, and so on. I don't care how many terms you give me. So I'm guaranteed that the power series that this function is the sum of is 1 plus 2x plus 3x squared. Let's say, for argument's sake, they told us to show the first 4 non-zero terms. Well, we come back up here and we pick up the next term, which we know had to have been x to the 4th. So we know the derivative of that was 4x cubed. So there we are. So not difficult at all. Whatever operation has been done on one side of the equal sign, as long as we'll perform that same operation on the other side, we're guaranteed to get the correct power series. Let's try it one more time. Now we have 1 over 1 plus x. And so we want to know what is the relationship between those two functions. How do I start here and perform a mathematical operation and wind up here? Well, hopefully you can see the integral. Do you see that that is the integral of that function? Using u substitution, we're going to get the integral of 1 over u du. That gives us the natural log of u plus c. So what we're going to wind up with here is the natural log of the quantity 1 plus t, and we're going to evaluate it from 0 up to x. And so I'll hop down here. We have the natural log of 1 plus x minus the natural log of 1 plus 0. That term equals 0. So the result is the function that we're after. So since we know integration is the mathematical operation that we want to do, then what we're going to do is we're going to show that we know that this will yield us the natural log of 1 plus x. And therefore, we want to show that we realize that the result of that integral will yield us the power series for the natural log of the quantity 1 plus x. So let's do that. Let's find the antiderivative. We're doing it with respect to t. So make sure you're careful with your notation in this context. We have the upper limit Oh, wow. Drop the ball on that. Also drop the ball on notation. Goodness. Correct your notes. Make sure it looks like that. So there's the upper limit minus the lower limit, which is 0 minus 1/2 0 squared plus 1/3 0 cubed minus 1/4 0. Every term to infinity has a t in it. So when I substitute 0 in for that t, every term there is going to 0. Hang on a second. Trying to go too fast here. Please make sure that's in your notes. So we recognize that the power series for this function has to look like this because we did the same mathematical operation to both the sum of the original power series and each term in the original power series. Okay? You can see, just as it did for me, this can be a notation nightmare. So make sure you're meticulous with that notation. And I will be watching for that when it comes quiz and test time. Find the power series representation for e to the quantity x minus 1 squared. Well, I'm going to do something here that I can't do on very many functions. But because e to the x, which looks like so, we saw this on prior lessons, I know that the power series expansion for e to the x looks like so. I've generated it enough times, I know that that's what it looks like. Well, if I start there and I do some mathematical manipulations here to this function, so that step by step by step, I get to the function above. Now I'm going to take every x and I'm just going to square it. Okay? And then the next step that I would do is everywhere that there was an x, I would put an x minus 1. Now, this is a series, a power series, centered at x equals 0. This is a power series centered at x equal 1. It is a really bad idea to try to just manipulate your function and therefore do the same manipulations on the right-hand side of the equal sign to come up with your new power series from a Maclaurin to a Taylor, or from a Taylor to a Maclaurin, or even from a Taylor to a Taylor that's built around separate center points. So hence my warning down here. I want to give you a warning. This is not something that we can always do. You cannot use this technique for building a Taylor power series from a Maclaurin. One is centered around 0. This other one is centered around 1. You'd have to build them separately, which is something we can always do. But anything that saves us time in a timed test situation is something we're going to do. This states that the only exception to being able to do this is e to the x. That's not true. There are other exceptions. Other functions behave in such a way where we could do it to them as well. E to the x is the only one I've ever seen on the AP exam. So it's the only one that I want you to think about doing this to if you're on the AP exam or in an exam situation. I'm about out of time on this video. I'll finish this example on the next video.